In Chapter 10, we'll be looking at reactions with alkynes. What is shown here is an Alzheimer's drug, which is called selegiline, and you can see here there is an alkyne functional group in there and also a center of chirality. If you remember all the way back to Chapter 1, when we looked at different bonds and orbitals, we saw that alkynes have a carbon-carbon triple bond. Within the triple bond, there is one sigma bond and two pi bonds. We can see that head-on sigma bond here and the two pi bonds at those sites there. Within the carbon-carbon triple bond, we get one sigma bond and two pi bonds. Altogether, there is a lot of electron density, which we can see if we look at the electrostatic model here. The areas around the carbon are very red, so this is a very nucleophilic center, which we can use to do several reactions. Acetylene, which is shown here and here, is the most simple alkyne that you can have, and that is often used, as you can see here, for blowtorches, and it's also used as a precursor for the synthesis of more complex alkynes. This ethynyl estradiol is an example of an alkyne as well, and that's in many birth controls. There's two types of alkynes. If the alkyne triple bond is on the end, that's a terminal alkyne. If it's in the center and there's carbons on either side, this is an internal alkyne. And one thing that you'll notice with all of these is that the bond angles are 180 degrees. So be sure to draw them that way. When we're looking at alkyne nomenclature, it is very similar to that of alkene nomenclature, except that we change the ending from "ine" to "eine." So we're going to name the parent chain, which should include the carbon-carbon triple bond. We'll look at the substituents, assign a locant. Again, we're going to give the carbon-carbon triple bond the lowest number possible. Then we number the substituents and name it in alphabetical order. And the carbon-carbon triple bond is going to be placed either just before the parent name or just before the "eine" suffix. We're looking at the parent here. This is already numbered for us. So this would be a heptyne. And there's two methyl groups here and there. So we can have 5, 6 trimethyl, 2 heptyne, or you would have 5, 6 trimethyl hept 2-ine. We want to include the alkyne in the parent name. So for this one here, even though the longest parent chain is 1, 2, 3, 4, 5, 6, 7, 8 carbons long, we want to include the parent here. So this would be 3 propyl heptyne. So we can go ahead and look at how we would name these. In this example here, you want your alkyne to have the lowest numbering. This would be 4,4-dichloro, 2-hexyne, 3-isopropyl, octyne, and here the alkyne is coming off. We want to include that in the longest carbon chain. So here we have an ethyl, propyl, and a methyl. For ethyl, 5-methyl, 3-propyl heptyne. So when you're drawing alkynes, I like to start with the triple bond so I know where my angles are going from. So here's my triple bond. It starts at 2, so I have 1 on the other side. This is 3, so 1, 2, 3, 4, 5, 6, 7. At 2 here, 1, 2, 3, 4, 4 dimethyl, and 5 ethyl. That starts there, 8. So this is 9, 10, 5, 4, 3, 2, 1. 2 methyl, 5 methyl, 9 methyl. If there's an ene here, this is decene, so I also have a double bond at the second carbon. So that would be how we did 2,4,2,5,9 trimethyl, 2-decene, 7-ine. Alkynes are acidic compared to alkanes. If you recall, the pKa of an ethane is around 50. For an ethylene proton is around 44. And for acetylene, it's around 25. If we have a strong enough base that can go fishing for the proton, the electrons go on to the carbon. And this is an acetylide ion. Acetylene is a much weaker base than water, so we need a strong base to make it react, and we can't use that as a solvent. If you tried to do this reaction with water, the acetylide would just grab a proton from the water and you would get the acetylene back. There's different ways that we can make alkynes, and it's similar to what we did in the last chapter. Previously we had a strong base which could grab a proton, and we would get this alkene here. Now we have a strong base and an alkyl dihalide, and we form the alkyne. So it can be prepared by elimination. Geminal halides can be used where the bromines or the halogens are both on the same carbon. First we do an E2 reaction. The base goes fishing for the hydrogen. Those electrons come here and kicks off a Br, and notice that it's anti-coplanar. So there's a double bond there, and the base can now grab this proton and do the same mechanism. And they end up with the triple bond. We can also use a vicinal dihalide where the carbons are next to each other, and this would be happening in the same fashion with the strong base. If we form the acetylide, we have sodium with the acetylide here. That can grab the hydrogen. So water is a stronger acid. This is a stronger base. This is the weaker acid. Plus the weaker base. So your equilibrium lies in favor of this side. A base that you would use to do this reaction is sodium amide and ammonia, and you want to use this excess. Excess means that we have an excess of that. So that would be the multiple equivalents that you need to form the triple bond. And we would get that product. We can reduce alkynes. In chapter 8 we saw that if we added hydrogen over a metal catalyst with the alkene, we would get the alkane. That happens in 100% yield. If we do the same thing with the alkyne, we also get the alkane in 100% yield. So with H2 platinum, we first go through this cis because it adds syn, goes to the cis intermediate, then we have H2 platinum sitting around, and we get the alkane. If you want to stop at the double bond, then you need to have a poison catalyst, and that will selectively react with only the alkyne, and it will stop at the double bond. So if we have this poison catalyst, It will stop at the double bond and it will give us a cis double bond. The catalyst that we use is called Lindlar's catalyst, and you can see the structure here, and those are generally the conditions that you would use to do this poison catalyst. But as long as you write Lindlar's or Lindlar's catalyst under there to indicate the catalyst that is being used, then we know that that's going to be the catalyst. So you don't have to remember all of these things on this side, just that it's Lindlar's. So for this one, we're selectively going to react with the alkyne only. This double bond stays the same. And then we get a new double bond forming there. If you want a trans double bond or an E double bond, then we have to use a different reagent. This one is sodium metal in liquid ammonia. And you get the E double bond in 80% yield. And the way that this works is through a radical mechanism. And radical meaning that it's a single unpaired electron, and you can notice here that the arrows have a single barb, so one electron is moving at a time. The sodium will act with the triple bond here at this carbon. One electron will come over here, one here. So then we have a pair of electrons here, or a negative charge, plus the one radical. And it goes into the opposite trans because this is lower energy. There's less electron repulsion here, which is high energy. That's how we get to the trans double bond. So once we form this, this can grab a hydrogen. There's a hydrogen there, and we still have that unpaired electron. And the sodium radical can pair up with that electron. So there's our lone pair there now with a negative charge. And that can grab a hydrogen. And you get your alkene. If we look at a couple of reactions with a poison catalyst, we have sodium, which is our reagent that will give us the trans or E double bond. You can just count the number of carbons. There's 6 there. And the double bond starts at 3. So that would be the product there. The liquid ammonia with sodium metal will not do anything with this double bond here. And again, we'll make a trans double bond. So double bond at 2 and 5. Then we have 7, 8. And just a summary of reactions. If you have an alkyne with hydrogen and palladium, or platinum, we get the alkane. If we use this with Lindlar's catalyst, we get the cis double bond. With sodium and liquid ammonia, we get the trans double bond, and either of these alkenes with H2 platinum gives us the alkane again.